June 29, 1995. It is 5 p.m. in Seoul, South Korea. On the 5th floor of the Sampoong Department Store, a civil engineer looks at a crack in the ceiling that has widened to 10 centimeters. He tells the chairman of the Sampoong Group that the building is in imminent danger of a progressive collapse and must be evacuated immediately. The chairman refuses. 52 minutes later, a critical column in the south wing loses its remaining structural capacity. The building falls to the ground in under 20 seconds. 2,000 people are inside. 502 of them die. We are going to examine the mechanical reality of the deadliest peacetime building failure in South Korean history. According to the 1996 Ministry of Construction White Book, this disaster was a mathematical certainty. It was the final point on a curve that had been bending toward failure for nearly 5 years, driven by a documented history of unchecked structural alterations. To understand how a modern commercial structure simply drops out of the sky, we have to look past the final moment of collapse. We need to work backward through the mechanics of punching shear and track the specific human decisions that guaranteed it. This 3D skeletal model shows the baseline design of the Sampoong Department Store. It was a flat slab construction. Notice the columns are spaced roughly 36 feet apart, and there are no auxiliary beams. The concrete floor slabs transfer their load directly into the vertical columns. That is the central design fact of this story. Originally, the site was zoned for a residential apartment block. When the chairman decided mid-project to build a department store instead, he ordered the contractors to remove several internal support columns to open up the floor plates for retail space and escalators. The original structural engineers refused, stating the load paths would fail. The chairman fired them and brought in his own in-house construction company to carry out the changes. This diagram illustrates the next critical alteration. The initial design specified reinforced concrete columns with a diameter of 80 centimeters. During construction, the columns actually built into the structure were reduced to 60 centimeters. That is a 25% reduction in cross-section. In a flat slab building without auxiliary beams, structural survival depends entirely on the joint where the slab meets the column head. The primary failure mode here is known as punching shear. Because the critical shear strength scales directly with the perimeter of the column, shrinking the diameter causes a sharp concentration of stress. It drastically increases the probability of a brittle failure, where the column punches straight through the floor above it. By cutting the column perimeter to save space and cost, the building's core load-bearing capability was already operating near its strict mathematical limits before the first customer ever walked through the doors. Then, the use case changed. The initial blueprint called for a roller skating rink on the 5th floor, a relatively light occupancy. But after construction, management decided to convert that space into a row of traditional Korean restaurants. This split-screen comparison shows the difference in mass. On the left is the light wooden flooring of a skating rink. On the right, the restaurant conversion requires a thick concrete topping embedded with heavy hot water radiant heating pipes. Customers sit directly on the floor, so this heating system is mandatory. This single design change roughly doubled the dead load sitting on the 5th floor slab, and none of the reduced 60-centimeter columns directly underneath it were ever strengthened to carry that extra weight. 2 years later, 3 large air conditioning units, weighing 15 tons each, were installed on the roof. Standard procedure requires a crane to place equipment of this scale. Instead, to save money, the units were dragged across the roof slab from one side of the building to the other. The sheer friction of dragging 45 tons of machinery cracked the roof slab directly above a specific support pillar, column 5E. Management patched the surface cosmetically. They left the units in their final position, where their operational vibrations spent the next 2 years continuously working those structural fractures wider. The flat slab system was now pinned between 3 compounding forces. It had heavily reduced shear perimeters below, doubled dead loads sitting on the 5th floor, and unaddressed dynamic stress fractures propagating down from the roof. By April 1995, those cracks became visible on the 5th floor ceiling. On the morning of June 29th, the final day, the facility manager walked the 5th floor and found an inch-wide separation opening along the concrete slab edge near column 5E. This animation shows what happened next. At 1 p.m., loud bangs echo from the upper structure. In response, management turns the rooftop air conditioning units off. Those bangs were not the building settling. They were the sound of sequential failure. The concrete slab was actively tearing its own internal steel reinforcement apart, attempting to redistribute the load laterally away from the failing zone around column 5E, pushing that stress onto neighboring columns that were just as weak. At 3 p.m., an emergency structural engineer arrives, inspects the damage, and tells the chairman to evacuate the entire store. But the late afternoon shopping rush is starting. Management opts to move some merchandise to the basement, patch the new cracks with plaster, and keep the doors open. They treated an active, audible shear failure as a maintenance nuisance. The store was generating $500,000 a day, and the executive team chose to protect that revenue stream rather than the 2,000 people shopping and working below. When investigators later analyzed the collapse for the 1996 White Book, they found a distinct discrepancy in how international building codes predicted the building's survival. This data table compares the 3 analytical methods used by the inquiry. The American code, ACI 31889, actually predicted no failure under the as-built loads, due to differing assumptions about reinforcement detailing. But the British code, BS 811085, and the Gardner 1996 method, which was specifically calibrated to flat slab punching shear, both correctly showed a very high probability of failure. At 5:52 p.m., the math finally resolves. The structural degradation at column 5E reaches its limit. The column punches completely through the weakened 5th floor slab. The flat slab loses its support and drops massively onto the 4th floor. That heavy kinetic impact instantly overloads the floor below it. The 4th floor drops onto the 3rd, and the resulting progressive collapse cascades through 5 floors of the south wing in roughly 20 seconds. The collapse of the Sampoong Department Store was a chain of recoverable errors. The disaster was built sequentially by passing standard engineering gates, starting from a dimension cut on a construction blueprint in 1988 to a dragged air conditioner in 1993, right up to a direct, ignored evacuation warning at 3 in the afternoon. At any point during those 5 years, and right up until the final hour, basic engineering judgment could have broken the chain and saved the 502 people inside. If you found this breakdown useful, the channel covers structural and aviation failures of this kind every week. There are companion analyses on the playlist for the Hyatt Regency Walkway and the FIU Pedestrian Bridge, which cover similar themes of incremental design.